Welcome back, dear all, in our next session on displacement, velocity, acceleration and jerk calculation and drawing the graph for the follower in a cam mechanism moving with simple harmonic motion. Before moving ahead, I insist you to please watch this video by kinematics with microstation CH07D SHM cams by Mr. Ujjwal Rane, which is available on YouTube. So once you see this video, so it will be easier for you to understand my lecture. Now displacement of the follower moving with SHM is given by this equation: y is equal to s by 2 under bracket 1 minus cos pi by theta o into theta whole bracket close, where s is the displacement, theta o is the angle turn during outstroke, and theta is angle turn during outstroke. So this theta is variable. It may vary from 0 up to theta o. So this theta is a variable and all other parameters are constant. So s and theta o are constant, whereas this theta is variable. It is during outstroke. During return stroke, only difference is instead of theta o we'll have theta r. Theta r stands for return stroke and o stands for outstroke. So the displacement of the follower moving with simple harmonic motion, its displacement graph you can observe and you can learn from the video of Mr. Rane, as I had shown in the earlier slide, or you can search on the YouTube. So there are many videos available how to plot the displacement graph in a cam mechanism moving with simple harmonic motion. So instead of that, I will concentrate on the further part of velocity graph, acceleration graph and jerk graph that is difficult to understand. So displacement graph you have to learn from the other videos. I will teach here the acceleration, velocity and jerk graphs. So this is the displacement equation, and the displacement graph, it will come like this. It is its angle turn is shown on the x-axis, whereas the displacement of the follower is shown on the y-axis. And its proper guidance how to plot it you will learn from Mr. Rane's video or someone else's video. There are many videos available how to plot displacement graph moving with simple harmonic motion, so you can see from the YouTube. I will concentrate on the further part, that is calculation, formula and velocity, acceleration and jerk part. So the velocity, as we know, the rate of change of displacement with respect to time is called as velocity. So while displacement equation was there, if we differentiate that equation, we will get this equation, that is velocity is equal to pi by theta o into s by 2 into omega into sine of pi by theta o into theta. So this is theta o is angle turn during outstroke, s is the displacement of the follower during outstroke, and this theta is a variable angle. So you can calculate velocity at any given angle during the outstroke by using this formula. Now velocity at the start of outstroke. So velocity at the start of outstroke means at the start of outstroke, what should be the velocity? At the start of the outstroke, the angle turned is 0. If angle turned is 0, here theta is angle turn. So if you put 0 over here, so we will get the equation as this part of the equation, sine of pi by theta o into 0. So it will become sine 0, and sine 0 we know its value is 0. So the entire equation multiplied by sine 0, that is 0, will lead to 0. So at the start of outstroke, the velocity will become 0. So whenever you are going to do the calculation for velocity or acceleration or jerk in simple harmonic motion, first thing you need to do is just put the value of the angle turn in the trigonometric function and see whether the trigonometric function becomes 0 or not. If it becomes 0, then your further it becomes 0 or not, your further calculation will become easy. So sin 0, it will be 0 at the start of outstroke, means at the start of outstroke velocity is 0. So put the value over here, 0 over here, you will get sin 0. Sin 0 means 0, so the entire term will become 0. So at the start of the outstroke velocity will be 0. Velocity at the middle of outstroke. Now at the middle of outstroke means angle turned is half of outstroke, that means theta O by 2. As it is theta O by 2, so put theta O by 2 over here in this equation. Only calculate this term first. So sine of pi by theta O into theta O by 2. So theta O will get cancelled. We will get pi by 2. And sine of pi by 2, that means sine of 90 degrees. Sine of 90 degrees is 1. So this trigonometric part will become 1. And what we will get is pi velocity equal to pi by theta O into s by 2 into omega. So it is pi by theta O into s by 2 into omega. So one thing you should remember here, and you must remember over here, this theta O in this equation, or this theta O in this equation is out of trigonometric function. That's why this theta O must be in radians, whereas this theta O, it is inside trigonometric function. As it is inside trigonometric function, it must be in degrees. This theta is also inside trigonometric function, that's why it must be in degrees. So you should remember this. Inside trigonometric function, any angle term will always be in degrees, and out of trigonometric function it will always be in radians. So you should remember this part. Now velocity at the middle of outstroke we had seen. Now velocity at the end of outstroke. So velocity at the end of outstroke means when angle turned is theta O. So in this sine function, if you put the value, if we term the value as theta O over here, so we put theta O over here, then what you'll get is pi by theta O into theta O. So theta O will get cancelled, and what will remain is sin pi. Now sin pi or sin 180 degrees is 0. That's why this trigonometric part will become 0, as the entire equation is in multiplication with this trigonometric part. So the entire equation will become 0. So we'll get sin pi, and sin pi is 0. That's why velocity at the end of the outstroke will become 0. Now velocity of the follower during return stroke moving with simple harmonic motion. Now what are the differences? You can observe here. There is a minus sign over here. In the previous equation there is no minus sign, as the velocity is a vector term. So if during rise you are taking velocity as positive, then during the return phase you must take velocity as negative. That's why it is minus over here. And the other difference is wherever there is theta O, that is angle turned during outstroke in the previous equation, it will be replaced with theta R, that is angle turned during return stroke. Remaining all part is same. So angle turned by follower during return stroke. Now first part is at the start of return stroke. So at the start of return stroke, as we have seen earlier, this pi by theta R into 0. So it will become 0. So sin 0 is 0, and the entire equation will become 0. So at the start of the return stroke, again the velocity will become 0. In the middle of the outstroke, theta will be replaced by theta R by 2, and theta R will get cancelled. What will remain is sin of pi by 2. Sin of pi by 2 is 1. So the equation will be like this, sin of pi by 2. So minus pi by theta R into s by 2 into omega. And at the end of the outstroke again, at the end of return stroke again, instead of theta we have to put theta r. So theta r will get cancelled, and what will remain is sin pi. Sin pi is 0, that's why the entire equation will become 0. So velocity at the end of return stroke will again become 0. So you can observe here, velocity at the start and at the end of the out stroke as well as return stroke 0. Only velocity we are getting is at the middle of the outer stroke as well as at the middle of return stroke. So velocity at the start and end will be 0. Similarly, same thing we had seen in case of uniform acceleration and retardation motion. Same thing is here in the simple harmonic motion, that is velocities at the start and end of the outer stroke as well as return stroke will become 0. Only you have to calculate the velocities at the middle of the outer stroke as well as at the middle of return stroke. So that's how we are going to plot it. This is the displacement graph. You are going to learn through Mr. Rane's video in the displacement graph. It is not that much accurate. So from the Mr. Rane's graph you can see the actual video. Now how to plot it? So velocity on the y-axis, on the x-axis there is angle turn theta o. So first part is angle turn during outer stroke theta o, then there is 12, then angle turn during return stroke, that is theta r. At the start velocity is 0, at the end of the outer stroke velocity is 0, at the start of return stroke velocity is 0, at the end of return stroke velocity is 0. Only velocity is positive at the middle of outer stroke, so its equation is pi by theta o into s by 2 into omega, whereas in case of return stroke it will be minus pi by theta r into s by 2 into omega. So only at two places you have to calculate the velocity, at the middle of outer stroke and at the end of middle of return stroke. Remaining all 4 points are 0 over here. So these are, you have to plot it. So you have to plot the velocity with the help of a smooth freehand curve. So from the start till the middle and till the end you have to plot it like this, and from the start to the middle and till the end you have to plot a smooth freehand curve to represent the velocity. Here it won't be constant, as velocity won't be constant because velocity is slope of displacement graph, as displacement graph is varying as it is a curve. That's why the velocity varies from start of the outer stroke till the end of outer stroke, and displacement is varying from the start of return stroke till the end of the return stroke, and its slope is never constant at any position. That's why the velocity won't be constant, and velocity we have to represent it by a smooth freehand curve for the outer stroke as well as during the return stroke. Now next part is acceleration of the follower moving with simple harmonic motion. As we know, the acceleration is rate of change of velocity with respect to time, or differentiation of velocity equation with respect to time. So once we differentiate that equation, this is the velocity equation, and we differentiate with respect to time. So we can observe here pi by theta o, it is a pi constant, theta o is constant, s by 2 is also constant, omega is constant. So entire this term is constant, that's why that will be kept out. And the differentiation of sine is cosine. So cos of pi by theta o into theta, but theta is also a variable over here. As theta is a variable, so differentiate theta with respect to time. So it is d theta by dt and multiply by this constant, so pi by theta o. So we will then get this equation. So further, d theta by dt is rate of change of angular displacement with respect to time, that is nothing but angular velocity. So pi by theta o into pi by theta o, we will get pi square by theta o square, s by 2 will be same, omega into d theta by dt, that is omega, that means it is omega into omega, that is omega square, and cos of pi by theta o into theta. So we'll get the acceleration equation like this. Now let's find acceleration at three different positions: at the start, at the middle, and at the end of outstroke as well as return strokes. So this is the equation of acceleration. Now at the start of outstroke, angle turn during outstroke is 0. So instead of theta we have to put 0. So this entire term will become 0 and this will become cos 0. As we know, cos 0 or cosine of 0 is 1. That's why acceleration will be, as we will get cos 0 over here. So acceleration will become only this constant part. So pi square upon theta o square into s by 2 into omega square when angle turned is 0. Now at the middle of outstroke, so at the middle of outstroke, the angle turn is theta o by 2. So we will put theta o by 2 in this equation, only this part in the cosine part. So theta o by 2 if you put, so theta will get cancelled and what will remain is cos of pi by 2 or cos 90 degrees. As we know, cosine of 90 degrees or cosine of pi by 2 is 0. So this term will become 0. As this term will become 0 and it is in multiplication of remaining part, so at the middle of outstroke acceleration will become 0. So you can observe here in this equation, pi by theta o into theta o by 2, theta o will get cancelled and what will remain is cos of pi by 2. Cos of pi by 2 is 0. That's why this entire equation will become 0. At the end of outstroke, so at the end of outstroke we have to put theta as theta o. As we will put theta as theta o, so theta o will get cancelled and what will remain is cos pi. We know cos pi is minus 1. So just observe here in this equation, we have to multiply, we have to replace theta by theta o. So theta o will get cancelled and what will remain is cos pi in this trigonometric part, and cos pi is minus 1. So acceleration at the end of the outstroke will remain pi square by theta o square into s by 2 into omega square multiply by minus 1. So we'll get this equation. So at the start of outstroke and at the end of outstroke, the equation of acceleration is same, only difference is the sign. So at the start it is positive, at the end it is negative, and in the middle it is 0. So only thing you have to do while doing the calculation is calculate only at the start, and at the end the same value will be repeated but its value will be negative. In the middle it is already 0. Now follower moving with simple harmonic motion during return stroke. So during return stroke, just observe here, the equation is same as that in the outstroke, only difference is minus sign. As acceleration is also a vector quantity, so acceleration during outstroke, if you are taking it as positive, then during return stroke it must be taken in as negative. So its a sign indicates only the direction. The minus sign indicates its a direction is in the return phase. The other variation in the equation is, instead of theta o, that is angle turn during outstroke, only we have to put as theta r, that is angle turn during return stroke. Remaining all things are same. So again we have to calculate it at three different positions: at the start, in the middle, and at the end of return stroke. So at the start of return stroke, theta is theta equal to 0. As theta equal to 0, so we will get cos 0. Cos 0 is 1. So the equation will be minus pi square by theta r square into s by 2 into omega square. Now at the middle of return stroke, so at the middle of return stroke, theta will be theta r by 2 and it will become cos of pi by theta r into theta r by 2. Theta r will get cancelled, and what will remain is cos of pi by 2. As cos of pi by 2 is 0, so this entire term will become 0, and it will be in multiplication with other factors, so the entire equation will become 0 at the middle of return stroke, similar to the out stroke. So it will be 0. Now acceleration at the end of the return stroke. So acceleration at the start of return stroke, its equation is this with the minus sign. So acceleration at the end of return stroke, the equation will be same, but its sign will be invert of this sign, means that will be positive, as we had seen earlier during the out stroke. So similarly we can put the values out there, that is, instead of theta we have to put theta r. So theta r and theta r will get cancelled. What will remain is cos pi. Cos pi is minus 1. So minus and minus 1 will get cancelled, and what will the equation will get is the same equation with a different sign. Now next part, that is graphical plotting. So at the start of out stroke, acceleration is positive, its equation is written over here. In the middle of the out stroke, acceleration is 0, and at the end of the out stroke, the value of acceleration is same as the start of the out stroke, but it's negative. So plot at the end. So at the start positive, in the middle 0, and at the end a certain negative value. Similarly, at the start of return stroke, acceleration is negative. In the middle of return stroke, it is 0. At the end of return stroke, it is having certain constant positive value. Now how to plot the graph? So you can observe here, the velocity is not a straight line, it is a curve over here. As it is a curve, that means its slope is varying. So slope of velocity graph, if it is varying, then definitely the acceleration is varying, because acceleration is differentiation of velocity with respect to time, or acceleration graph is slope of velocity graph. As slope is not constant, so acceleration is not constant, that means we can't represent it with a straight line, so we have to represent it with the help of curves. So draw the acceleration graph with the help of smooth freehand curves. So at the start it is positive, then it becomes 0, at the end it is certain constant negative value. Then the dual starts. At the start of dual, as there is no velocity, if velocity is 0, then definitely acceleration is 0. So here the acceleration becomes 0, so we have to plot a vertical line over here. Now at the start of return stroke, from as there is a dual part over here, so at the start of the return stroke, velocity was 0. As velocity was 0, that means there was no displacement and there was no acceleration. So it was 0 initially, and then at the return part starts, so it attains certain constant negative value of retardation or negative acceleration. Its magnitude is written over here, its magnitude formula is written over here, minus pi square upon theta r square s by 2 into omega square. Then at the middle it is 0, at the end it is certain constant value, pi square upon theta r square into s by 2 into omega square. So at the end of return stroke, you can observe here again the velocity becomes 0. As velocity becomes 0, that means the acceleration is also 0. So at the end of the return stroke, acceleration will become 0. So certain constant value of acceleration to 0 value over here. So we have to draw a vertical line over here. Now next part is jerk. So jerk, we know rate of change of acceleration with respect to time is jerk, or differentiation of acceleration equation with respect to time is jerk equation. So differentiate the above equation or acceleration equation, will get this equation. Now again you can observe pi square upon theta o square, s by 2 and omega square. All these terms are constant. That's why this will be out of the differentiation function, and only differentiation we have to do is of this part. So cosine, differentiation of cosine is minus sine pi by theta o, so it will be constant, but theta is a variable over here, so we have to differentiate of the angle part also. So what will remain is this part is constant, differentiation of cos is minus sine, and differentiation of this function, so pi by theta o into d theta by dt. D theta by dt is omega or angular velocity, so we will get pi square upon theta o square into pi by theta o, so we will get pi cube by theta o cube into s by 2, and to omega square into d theta by dt, that is nothing but omega, so we will get omega cube. So we will get this final equation, minus pi cube upon theta o cube into s by 2 into omega cube under bracket sine of pi by theta o into theta. Again you need to remember one thing, that this theta o is out of trigonometric function. As it is out of trigonometric function, so it must be in radians, whereas this theta o and theta are inside trigonometric function, that's why they must be in degrees. So let's calculate the jerk at all the 6 positions, that is at the start, at the end of outer stroke as well as the return strokes, and at the middle of outer stroke and return strokes. So jerk of forward moving with simple harmonic motion, its equation we had just derived. So at the start of outer stroke, means theta is 0, so we have to put theta is 0 over here. Once we put theta 0 over here, so this part will become 0, and what will remain is sine 0. As we know, sine 0 is 0, that's why this entire term multiplied by 0 will become 0. So at the start of outer stroke we will get jerk as 0. At the middle of outer stroke, theta will be theta o by 2, so this theta will be replaced by theta o by 2, and what will remain, theta o will get cancelled, and what will remain is sine of pi by 2. So theta o will get cancelled, and what will remain is sine of pi by 2. Sine of pi by 2 is 1, so this entire trigonometric part will become 1, and it will be multiplied by minus pi cube by theta o cube s by 2 into omega cube. So this equation we will get at the middle of outer stroke. Now at the end of outer stroke, put theta as theta o, so theta o will get cancelled, and what will remain is sine pi. As we know, sine pi is 0, so this trigonometric part will become 0, and this entire equation will become 0. So at the end of outer stroke, jerk will again be 0. Similarly for the return stroke, the equation is same, as the jerk is differentiation of acceleration with respect to time. Jerk is also a vector quantity, so it represents magnitude as well as direction. In outer stroke, as the direction or the equation was negative, so during return stroke this equation must be positive, because minus sign indicates the direction and plus sign is also indicating the direction. During outer stroke, if jerk is negative, then during return stroke jerk will be positive. So the same equation of jerk but with the positive sign, and instead of theta o we have to write here as theta r. So theta r over here and theta r over here, and remaining all the terms are same. So we have to calculate the jerk at 3 different positions. At the start of return stroke, so we have to put theta as 0. If you put theta as 0 over here, we'll get sine 0. Sine 0 will be 0, so entire equation will become 0. So jerk at the start of the return stroke will be 0. Now next part is jerk at the middle of return stroke. So instead of theta we have to put theta r by 2. Theta r will get cancelled, and what will remain is sine of pi by 2. Sine of pi by 2 is 1. So we'll get jerk as this part of equation. So pi cube by theta r cube into s by 2 into omega cube. Now jerk at the end of return stroke. So at the end of return stroke, theta will become theta r. So theta r will get cancelled. What will remain is sine pi. Sine pi is 0. That's why the entire equation will become 0 at the end of return stroke. So at the end of return stroke, we'll get jerk as 0. Now let's plot jerk during out stroke and return stroke on a graph. So at the start, jerk is 0. In the middle of out stroke, jerk is having certain constant negative value. At the end of out stroke, jerk is 0. Again at the start of return stroke, jerk is 0. At the middle of return stroke, jerk is having certain constant positive value. At the end of return stroke, jerk is again 0. As you can observe here, the acceleration is a smooth curve. That means acceleration is not a straight line, or it is not a constant. If it is not a constant, means acceleration is varying, so its slope is also varying from different point to different point. As its slope is varying, that's why jerk will also vary from point to point. That's why jerk won't be a straight inclined line, but it will be a curve. So jerk will be a curve. Now one more thing you can observe here, jerk will be curve as we had discussed over here. So from the start till the middle till the end, jerk will be a smooth freehand curve. Similarly during return stroke, jerk will be a curve. So one more thing you can observe here is a straight vertical line over here. As jerk is a slope of acceleration graph, jerk graph is slope of acceleration graph, so this part will be okay. We will get a curve over here in the jerk graph, but at the start of the out stroke, from 0 value of acceleration to certain constant value of acceleration, it takes no time, and we have represented it by vertical line, and slope of vertical line is always infinity. That's why at the start of out stroke, we need infinite amount of jerk to attain this constant amount of acceleration. That's why at the start of out stroke, we have infinite amount of jerk in upward direction, as jerk is as acceleration is rising, so jerk will be positive. Now at the end of out stroke, again acceleration varies from certain constant negative value to 0 suddenly within no time. So it is represented by a vertical line, as this vertical line is having infinite slope. As vertical lines have infinite slope and infinite positive slope we are getting over here. So at the end of return stroke, again we have infinite amount of jerk required to achieve certain amount of deceleration or retardation to 0 value of acceleration. So infinite amount of jerk is required at the end of out stroke. Similarly, at the start of return stroke, again you can observe here, it is a vertical line, means its slope is infinity in downward direction. That's why jerk is present there in the downward direction, and its magnitude is infinity. So at the start of return stroke, infinite amount of jerk is required. Similarly, there is a vertical line at the end of return stroke. That's why infinite amount of jerk is required. You can observe here it is in downward direction. Similarly, it is again in the downward direction. So infinite amount of negative jerk is again required to achieve 0 acceleration from certain amount of constant acceleration. So we will get this graph. So we have to plot the jerk like this. That is a smooth curve for the out stroke as well as smooth curve for the return stroke. At the start and at the end of out stroke, there is infinite amount of positive jerk, and at the start and at the end of return stroke, there is infinite amount of negative jerk. So together the entire graph will be look like this: displacement graph, velocity graph, acceleration graph, and jerk graph. Remember, this displacement graph won't be like this. You have to plot it as per that will be shown in Mr. Rane's graph. Don't plot as 0, half and end and draw directly a smooth curve, but plot it accordingly. So we will end here. Thank you.